All right, assalamu alaikum everyone. Let's begin. So we were doing trigonometry, and today we are going to do, first of all, some more practice questions on proving identities, if you have any problems in particular. And then we will be discussing how to solve a specific type of equation where we have something like this, for instance, sine of theta plus 30 degrees, that equals 0.5, for instance. When you have something other than x or theta inside the angle, we will be learning how to solve equations like these today as well. So that's the plan for today. This is what we did in our last session. In the last session, we learned how to prove identities. We also discussed some tips that help you while you're proving identities. That's what we did yesterday. We did a couple of examples as well. Now, first of all, you can let me know if there are any particular questions from the worksheet in which you had problems. We could start by discussing those problems first. Does anyone have any questions from the worksheet on proving identities? No questions?
Sir, can you do question 14?
14, 1, 4?
No, actually 13. My mistake.
13, okay. P1, trigonometry. Okay, this one, question number 13.
Yes, sir.
Okay, let's have a look at this. You can also let me know if there are any other problems from the worksheet specifically on proving identities. And then after that, we will be discussing our next concept. All right, so we have to prove this identity. 1 plus sine x divided by cos x plus cos x divided by 1 plus sine x, that is identical to 2 over cos x. We have to prove this identity. Now, which side do we start from? We should start from the left-hand side because the left-hand side has different functions. It also has more number of terms. So the left side is more complicated. We start from the left-hand side. Now, what do you have to convert it to? We have to convert it to a form in which we only have cos, right? So we need to get rid of sine somehow from this. Okay, that's what we need to do. Now, these are the two identities that we have. We're going to have them in front. Sine square theta plus cos square theta. That is identical to 1. And tan theta is identical to sine theta or cos theta. These are the two identities, right? Now let's start from the left-hand side. 1 plus sine theta, 1 plus sine x divided by cos of x plus cos of x divided by 1 plus sine x. Now, since we want to make it a single fraction, that's what we have on the right side. This is what we have on the right side, 2 over cos x. We can take LCM here. Let's take LCM. If we take LCM, 1 plus sine x multiplies with 1 plus sine x here. And that gives us 1 plus sine x into 1 plus sine x. We can write that as 1 plus sine x whole squared. And then cos x into cos x. That gives us cos squared x. And in the denominator, we have the LCM. We just multiply these denominators. That's cos of x multiplied by 1 plus sine x. All right, that's what we get in the denominator. Now, let's simplify this further. We can expand the numerator. The numerator gives us, this is a plus b whole squared, right? So we can say a squared, which is 1 squared, that's 1, plus 2 into 1 into sine x, that's 2 sine x, plus sine x squared, which is sine squared x, plus cos squared x. And in the denominator, we have cos x into 1 plus sin x. Now remember what I said, you should not try to simplify the denominator very early in your working, because you have to look out for opportunities to cancel out something. And if you look at the final result that you want at the end, that's 2 over cos x. So what you need in the denominator is just cos x. So you want to somehow get rid of 1 plus sin x. So you would want to cancel it at some point. So it's not a good idea to simplify it. Just leave it in this form so that we can get this thing canceled out somehow and have only cos x in the denominator. That's what we want at the end. Okay, so let's keep the new denominator as it is. Cos of x into 1 plus sin x. Now in the numerator, we have, sorry, this was sine squared x. In the numerator, we have sine square x plus cos square x. What's that? That is 1. So we can write it as 1 plus 2 sine x plus 1. And in the denominator, we have cos of x into 1 plus sine x. Now, if we simplify the numerator further, it becomes 2 plus 2 sine x. And in the denominator, we've got cos x into 1 plus sine x. Again, keep in mind what you want at the end. And at the end, you want something like this, 2 over cos x. So only 2 in the numerator and cos of x in the denominator. Can you cancel 1 plus sin x out somehow? Well, it's pretty obvious now that if you take 2 common in the numerator, that would leave you with 1 plus sin x inside the brackets. And in the denominator, you've got cos x into 1 plus sin x. And now 1 plus sin x and 1 plus sin x, they get cancelled. And you're left with 2 over cos x. And that's exactly what we wanted to prove there. This is equal to the right-hand side. Is that okay?
Yes, sir.
Okay, that was question number 13 from the worksheet. Any questions on this, anyone? Okay, let's have a look at the next one then. So next is question number 32, you were saying? 32. Okay, so again, you have to prove something here. This is 32. Okay, so we say we have to prove this identity, right? Tan x plus 1 over tan x, that's identical to 1 over sin x cos x. Now that's interesting. Remember the thumb rules that we discussed earlier, which side we should start from? The side that has more different types of functions. The right-hand side has different types of functions, right? We have sine here, we've got cos here. Fraction is on both sides, so that's kind of equivalent. But the left side has more number of terms. The left side has 2 terms. The right side only has 1 term. So if you look at the number of terms, the left side seems more complex. If you look at the number of different functions that we have, the right side seems more complex. So there is some complexity on both sides. Okay, there's some complexity on both sides. In such problems, it's often a good idea to simplify both sides a bit, if you can. Okay, so let's see what we have here. Tan x plus 1 over tan x, that's the left hand side. We should always write them separately so that you know you can't take one terms from one side to the other. You can say this is the left hand side. And the right hand side is 1 over sine x into cos x. Now, since both sides are kind of slightly complex, do keep this option open that you can simplify both sides a bit. Okay, start from one side and see if you get stuck somewhere, then you can maybe try doing something with the other one as well. If you just look at it at this point, there is not much that we can actually do to this one. As in, what would we do? How would you simplify this? There's nothing very obvious here. Okay, so but the left hand side, these are two terms. So this is something that we can simplify. We could start by taking, for instance, LCM and see what we get from that. If we take LCM, that gives us no, I think that would not be a good idea. If we take LCM, we would have tan square x. Instead of that, since we want sine and cos here, it's probably a better idea to just convert it to sine x over cos x directly. Remember, this was a tip that we discussed when we did this concept yesterday, that when you have tan on one side, it's often a good idea to convert it to sine over cos right away if you do not have it on the other side. So you don't have to have tan on the other side. So in this case, it's going to make things simpler if you just convert tan to sine over cos right away. So in this case, if you do that, let's see what we get. Tan is sine over cos. 1 over tan, what would that be? You can write that directly as cos over sine if you want, or you can take one more step. You can say tan is sine over cos, and then cos goes to the numerator, and it becomes sine x over cos x plus cos x over sine x. And now if you take LCM, you can kind of get that form, right? You get sine x into cos x in the denominator. The denominator gets multiplied when you take LCM. That will give you sine x into cos x in the denominator. And then sine x into sine x, what's that? That's sine square x. Cos x into cos x, that is cos square x. Sine square x plus cos square x, that's 1. So we actually get that form directly. We did not have to simplify the other side. We got this directly. So 1 over sine x cos x, that is equal to the right hand side. So yeah, the key thing here was to convert tan to sine over cos very beginning. Okay, you could do it without that as well. You could, for example, try taking LCM first. Let's see what happens if you were to do that. If you took LCM first, let's see what happens. You would still be able to prove it eventually, but it's most likely going to take longer. If you took LCM directly first, you would get tan square x plus 1. And now you can convert it to sine over cos at this point, right? Because there's not much that you can do after this. There's actually a P3 identity that you can use here that kind of would make things very quick here, but you haven't done that yet. 1 plus tan square is actually the same thing as secant square, but you will learn that in paper 3. That makes it just a 2-liner. But since we can't use that here, you can if you already know that, by the way. But since most of you haven't done that yet, we are not going to use that. What do we do at this point? You can convert tan to sine over cos. So it becomes sine square x over cos square x plus 1 whole divided by tan x. Or in fact, this tan x can also be converted to sine x over cos x. And now in the numerator, we would have to take LCM for this. That would give us sine square x plus cos square x whole divided by cos square x. And then this whole thing divided by sine x over cos x. Right? Remember that rule. We have a fraction in the numerator. We have a fraction in the denominator. The denominator above is going to go below. The denominator below is going to go above and get multiplied. So we can take this cos x to the numerator. So it becomes cos of x into sine square x plus cos square x. And bring this cos square x to the denominator and multiply it with sine. So it gives you sine x into cos square x. Now, cos x gets cancelled with 1 power of cos in the denominator. So you have cos x, sin x into cos x left in the denominator. And in the numerator, sine square x plus cos square x, that is 1. So you have 1 over sin x cos x. So yes, you can prove it like this as well, but it made things slightly more complicated. Okay. So that will be another way of thinking about this. You could do it either way. Okay. Any problem with this? In this case, proving from the right hand side would actually be even more complicated because remember the identities that we have. Tan x identical to sine x over cos x. So Naima is asking if we can prove starting from the right hand side. We can do that, although that's going to be quite tricky. We can try that as well. Let's do that. So if we start from the right hand side, that would be 1 over sine x into cos x. And what we want at the end is something like this. Tan x, so keep this in mind, tan x plus 1 over tan x. That's what we want at the end. Okay, so if we started from the right hand side, now what we want to do is we want to convert it to tan. Now in order to convert it to tan, you would have to split it basically. Okay, so tan of x is identical to sine x over cos x. What we can try doing here is we can say, let's write tan x into cos x identical to sine x here. So instead of sine x, since we want to convert it to tan, we could try starting like this. 1 over tan x into sine x, sorry, cos x into cos x, another cos x. And that makes it 1 over tan x into cos square x. Now we want to get rid of cos square x from the denominator. In order to do that, we could, what could we do here? Tan x into cos x is sine x. Okay. 1 over tan x into cos square x. So one way to do this would actually be doing partial fractions, because you'll do this in paper 3. In order to go from left to right hand side, you have to take LCM. The reverse of taking LCM is actually called partial fraction, finding partial fraction, breaking a fraction into multiple parts. That's one way you can do it, but you haven't done that yet. Let me think of another way of doing this. If you want to take this to the numerator, you want either sine x or cos x in the numerator. So you can break that down into 2 parts then using that identity. Okay, so one idea could be, I'm just going to try if it works. One idea could be that you multiply and divide by something like this. Since you want to have tan x plus this separated, we could write it like this and then have a minus there. If you were to simplify this a bit, this gives us sine x over cos x plus cos x over sine x. So if we were to do the opposite of that, yeah. Okay, so yeah, so now uh, the way to do this would be, yeah, so that will work. So let's do this. Remember those two identities that you have? Sine square x plus cos square x, that's identical to 1. Tan x is identical to sine x over cos x. So what you'll do is, you'll say, this is 1, right? The idea is you want to split it into two parts like this. Tan x plus 1 over tan x. If you wanted to go from this to that other side, what you can do is you can write 1 as sine square x plus cos square x. Right? Sine square x plus cos square x is identical to 1, right? So instead of 1, you write sine square x plus cos square x. That introduces this plus sign that we needed. Okay? So instead of 1, we write sine square x plus cos square x. And now we break it down. We break the fraction down. We say this is sine square x over sine x into cos x plus cos square x divided by sine x into cos x. Okay? So instead of 1, we write we write sine square x plus cos square x. And then what we do is we break down the fraction like this into two parts. Right? This separate and this separate. We can break the numerator like this. Now, if we look at the first fraction, sine square and sine x, they get cancelled. What are we left with? We're left with sine x over cos x. And if we look at the second fraction, square here and this get cancelled, and we're left with cos x over sine x. And that becomes tan x plus 1 over tan x. And that is what you had to prove. But again, this is going to be complicated. How I got this idea was that I thought of what we did here and the step that we got here. Now, if you compare this step with this, you get the idea. Okay, so if you replace sine square x if you replace 1 with sine square x plus cos square x, that could work because that gets you to this point from which you can go backwards. But you see, in order to get that idea, I had to look at what I get from simplifying the left-hand side. So in this case, starting from the right-hand side would not be a good idea. What you can do, however, is simplify both sides a bit. So maybe get to this point and then compare that with this. And since these two are equal, you could say that is that. But yeah, this is how you could approach it if you start from the right-hand side. The problem was to introduce a plus sign in the middle, and that comes using this identity. Is that okay? So you see, there are many different ways of proving identities. From each side, you've got multiple ways. You could think of another way from this as well. You could actually do partial fraction. Those of you who have done paper 3, you could do partial fraction this as well to break it down. And that could also work, although yeah, in paper 3 as well, in fact, don't do this partial fractions. That's for later, maybe in university, but that could be another idea. There are multiple ways of doing it, right? So we've done 3 ways like this. Any issues with this? Does it make sense?
Yes,
Okay.
sir.
All right, let's do the next one. 32. Now let's look at 45. Okay, let's be quick about this now because I do want to discuss one more concept before we end. Acha, by the way, do you want to do part two of this as well? Part two is straightforward after this, right? Can you do part two?
Yes, sir.
Yeah, that'll become a quadratic equation in tan. You use the quadratic formula and then find the values using quadrants and basic angle. So hopefully that should be doable. Let's look at this. Question number 45. Okay, now which side do we start from? Again, it's going to be easier to start from the left-hand side because as we just saw before, breaking a single fraction into multiple fractions is always going to be more complicated. Here you have two terms, making them a single term is going to be much easier. And you also have two different functions here. On the right side, you only have one function, right? So using all of those rules that we discussed, the left-hand side is more complex. In this case, we definitely should be starting from the left-hand side. Now, if we start from the left-hand side, that gives us sine theta over 1 minus cos of theta minus 1 over sine theta. Now, again, keep the end in mind. What do you want at the end? You want everything converted to tan theta. And you have sine and cos here at this point. Okay. You have to make multiple fractions. You have to convert multiple fractions to a single fraction, right? Now, what can we do? We can start by taking LCM. That could be one starting point. Let's do that. Let's take LCM. Let's multiply sine theta and sine theta here like this. That gives us sine square theta minus 1 into this. That's 1 minus cos theta divided by 1 minus cos theta multiplied by sine theta. Okay, let's think about what we can do now. We have sine square theta minus 1 minus cos theta. We want tan theta eventually. Okay, so in the numerator, we've got sine square theta minus 1 plus cos theta. And in the denominator, we have 1 minus cos of theta. Now, what we want to do is we want to somehow get rid of 1 minus cos theta. We have a factor in the denominator, 1 minus cos theta. Remember what we want at the end? At the end, we want 1 over tan theta. Now, let me actually write down the right-hand side here as well. Right-hand side is 1 over tan theta. What is 1 over tan theta? It's basically cos theta over sine theta. If you have this in mind, it'll make your working a bit simpler. So you would know, okay, this is what you want at the end. If you get this, then you can convert that to 1 over tan theta. So in the denominator, you want sine theta. You have sine theta here. And in the denominator, in the numerator, you want cos theta. Then you can write it as 1 over tan theta. So keep that in mind. This is what we want. Okay. So that means we want to somehow get rid of 1 minus cos theta. Now, how do we do that? For that, we need to somehow factorize the numerator. How do you factorize the numerator? You can convert sine squared to cos, first of all. So we have everything in terms of cos only, because that's what you want in the numerator as well, only cos. So let's convert everything to cos. Sine square can be written as 1 minus cos square theta. And you have minus 1 plus cos theta divided by 1 minus cos theta into sine theta. And now 1 and minus 1, they get cancelled. And you're left with cos theta minus cos square theta. And in the denominator, you have 1 minus cos theta into sine theta. Now you can take cos theta common in the numerator. And that leaves you with 1 minus cos theta inside the brackets. And in the denominator, you have 1 minus cos theta multiplied by sine theta. 1 minus cos theta and 1 minus cos theta can get cancelled. That's what we wanted to do. We want to cancel that thing out. And now we're left with just cos theta over sine theta. And this we know can be written as 1 over tan theta. And that is equal to the right hand side. That is what we wanted to prove. Is that okay? Now, in this case, factorizing the numerator was not very difficult. Sometimes you also have to use middle term breaking. So for example, in the numerator, you could have something like this sometimes. Cos square theta plus 7 cos theta plus 12. You could have something like this. And in the denominator, you might have, for instance, cos theta plus 3 into something, into maybe cos theta. Now, if you want to get rid of one of these factors in the denominator, you can factorize the numerator. You can use middle term breaking. Think of it as a quadratic expression. You could break it down like this using middle term breaking. Cos square theta plus 4 cos theta plus 3 cos theta plus 12. And then that becomes cos theta into cos theta plus 4. Then you have plus 3 into cos theta plus 4. And that gives you two factors. Cos theta plus 3 into cos theta plus 4 in the numerator. And then you can cancel this out with this. So sometimes you also have to do middle term breaking like this. Okay. In this case, in this particular question, it was the factorization of the numerator was pretty straightforward because we only had two terms. We just take cos theta common from that. But sometimes it does happen that you also have a constant term and you have to use middle term breaking like this. That's also possible. So also keep that in mind. All right. Any questions on this?
No, sir.
No.
No, sir.
You can do the second part, right? You just replace this thing with 1 over tan theta, and then it becomes a simple equation that you can solve, right?
Yes, sir.
Okay. All right, now let's start with our next concept then. Now, this is very important. It's going to be useful in paper 3 later as well. You'll be using this a lot there. So you have to remember this for later as well. Solving equations involving angles other than theta or x. Now, what does that mean? We have learned how to solve equations like this for now. If you have sine x equal to something, equal to let's say 0.4, we know how to solve this. So of course, before this, we could have a more complicated equation like this, but the angle has always been theta for all the questions that we've done until now, right? It's either x or theta. So you would have sine x equals something at the end, or tan x equals something, tan theta equals something, right? But sometimes what happens is instead of x or theta, you have something else as the angle. So for instance, you might get an equation like this: sine of x plus 30, that equals something. Or maybe cos of 2 times x equals something. This is called a compound angle where you have something being added or subtracted. This is called a double angle. But for now, all you need to know is, what if you have anything other than x or theta? So you could have something being added or subtracted like this. You could have something multiplying like this inside. How do you solve equations like these? That's the question. Let's take an example. Let's say you have an equation that looks like this. Cos of theta plus 60, that is equal to 0.85. Let's say you want to solve this equation. Cos of theta plus 60. Let me write down write this down as a fraction maybe, or it's okay, 0.85. This is the equation that we want to solve, and we know that theta is between 0 degrees and 360 degrees. That's the angle that we have. Theta is between 0 degrees and 360 degrees. Now remember, the angle is not theta. The interval that we're given is for theta, but the angle is not theta. The angle is this whole thing. Theta plus 60, that's the angle. All right. The interval that we're given is only for this part, theta. Now, how do you solve this equation? Now, there are, again, multiple ways of doing this. One way of doing this is, and that's an easy way of doing this without confusing yourself too much, that is that you use substitution. How do you use substitution? Whatever is inside the brackets, you substitute that with another variable. So you say, let some other letter, let's say A, equals theta plus 60. Okay. Let A equals theta plus 60. Now, once you do that, the equation becomes cos of A equals 0.85. And instead of solving that original equation, you say, let's solve this equation instead. Now, this is something that you know how to solve, right? Because it's like just like cos of x being equal to 0.5. It's just one letter here. This is something that you've been doing for many days now. You know how to do this. Okay, so that's the idea. Whatever is inside the brackets, you convert that, you replace that, substitute that with another letter. In this case, we say let A equals theta plus 60, and you write the equation in that form. And now you just solve this equation. Okay. However, when you do this, you have to do another thing along with this, and that is the interval that we were given, that was in terms of theta. Now the equation is in terms of A. So you also have to find an interval for A, that what values of A are possible when you look for the angles from coordinates at the end. What is the interval for A? Interval for theta is from 0 to 360. What about the interval from A? How can we think about this? We can say, okay, theta is from 0 to 360. If theta is 0, input 0 here in place of theta. If theta is 0, what value of A do we get? A equals 0 plus 60, that's 60. So we say 0 corresponds to 60 degrees. Okay, so the lower limit of A, therefore, is supposed to be 60 degrees. And then similarly, if theta is 360, what about the value of A? Input 360 in place of theta here. What does that give you? A equals 360 plus 60, which is 420. So that is the interval for A. When you're looking for values of A at the end, this is the interval that you have to keep in mind, that A has to be between this interval. Okay. And now the rest of it is the same as before. You just solve this equation. How did you use to solve equations like these? You would find the basic angle first of all. So let's find the basic angle. You say cos of alpha equals 0.85. What's the basic angle? Cos inverse of 0.85. Can you tell me what that is?
Uh, 0.555 to three significant figures.
Notice the angle, it's in degrees. So your angle has to be in degrees, not radians. So you always when you're solving problems like these, please make sure to look at the top of your calculator. Make it a habit. Whenever you have angles involved in a question and you're using sine, cos, tan, always look at the top of your calculator and see whether it's D written or R written, and notice what you have in the question. In the question, you have degrees. You should have D written on top of your calculator. This is a very common error in the exam. You end up losing a lot of marks because of this. So make sure your calculator is in the right mode, okay? So what's alpha then? 31.79 degrees. Okay, that's the value of alpha. Was anyone saying something? Were you telling me the answer from this?
Yes, sir.
Okay, all right, thank you. So basic angle is 31.79. Okay, we find that angle. Now, let's make quadrants. Cos is supposed to be positive. Where is cos positive? Cos is positive in the first quadrant or in the fourth quadrant, ASTC, either the first or the fourth. That's where cos is positive. So alpha could either be here or alpha can be here. These are the two possible values of alpha. Okay, where do we have to measure angles from? From the positive x-axis. Let's see the angles that we can get from this. So the interval for A is positive. We only have to go in the anti-clockwise direction, right? We don't have to go clockwise. We only have to go anti-clockwise. This is the first angle that we get for A. What's that? A equals 31.79. But is that in the interval? We are solving for A, remember? The interval for A starts from 60. This is not an interval. So we are not going to consider this. Okay, this is not in the interval. The interval for A starts from 60. And we're finding the value of A right now. So we are going to ignore this value. This is not possible. Okay, so we go further. This is the next angle that we're getting. That is what we're actually going to consider. And that's 360 minus 31.79, which gives us 328.21. That's the value of A that we have. That's one value. But now notice the interval is going above 360. That means you also have to check if you get any angles after completing one full circle, right? Because the upper limit is more than 360. So we go one full circle and come back here again. What's that angle? That is 360 plus 31.79. That's 391.79. Is that in the interval? That's also in the interval. So we also have to consider this. These are the two values of A that we're getting. Now, if you could go any further, that would go above 420. So we can't go any further. These are the two values of A. Once you have found the values of A, now you put that substitution back. What was A supposed to be? A was supposed to be theta plus 60. So you say, okay, this is the value of A. What about the value of theta? If A is equal to this, that means theta plus 60 equals 328.21. And the value of theta turns out to be 268.2 from this. And similarly here, we say theta plus 60, that is equal to 391.79. Subtract 60 from that, and we get 331.8 degrees. These are the two values of theta that we get as our solutions. And you would see, once you follow this process exactly like this, the values of theta are automatically going to be in the correct interval. The interval was 0 to 360. So theta is turning out to be within that interval from 0 to 360. But adjusting this interval is important. If you did not adjust this interval, number one, you would miss out on this solution. If you were only looking for values up to 360, you would not consider that. And you would mistakenly consider 31.79 as one of the results for A. But that's not supposed to be one of the answers there, because the interval for A starts from 60. It doesn't start from 0. So adjusting that interval is very important. When you do substitution, you also have to adjust the interval accordingly, so you know what angles you are going to be looking for. Is this process clear to everyone? Any problem with this? This is a standard method now that you can use for problems like these. Let me know if there are any issues with this. Can I have raise of hands from everyone? So I know you're all still awake, haven't slept already. Hira and Aisha, are you there? All right. Okay, so that's how we solve equations like these. Let's have a look at one example quickly, then we end for today. Let's have a look at one example from the worksheet. Okay, this is question number 44 from the worksheet. Let's try this. Okay, the first part of this is also interesting. Let's do both parts. Question number 44. Okay, so it says find the possible values of x for which sine inverse of x squared minus 1 is equal to pi over 3, giving your answers correct to 3 decimal places. So you have sine inverse of x squared minus 1 that equals pi over 3. You have to solve this equation. Now, you can't really do this on your calculator, right? Sine inverse of x squared minus 1. You can't take sine inverse of x squared minus 1, right? So how do you solve this equation then? Any idea, quickly? What do we do with this? Sine inverse of x squared minus 1 equals pi over 3. How do we solve this?
We take sine to the other side, then we move -1 and then square root.
Yeah, so that's good. We take sine to the other side. We take sine to the other side. It's sine inverse right now. When it goes to the other side, it becomes sine. So you have x squared minus 1 equals sine of pi over 3. Just like if you have sine of x equal to something, 0.4, when the sine goes to the other side, it becomes sine inverse, right? If you have sine inverse right now, you can take it to the other side to make it sine. That's what we're doing here. Since we have x on the left side here, we can't find this one on our calculator. On the right side, we just have a constant. So we can just take sine inverse to the other side to make it sine. Now, what is sine pi over 3? You can do that on your calculator. Sine pi over 3 is going to give you under root 3 over 2. Now take 1 to the other side. That gives you 1 plus under root 3 over 2. That will give you some value in decimals. You don't want an exact answer. They're asking for answers correct to 3 decimal places. Now, since they've specified that they want answers in 3 decimal places, that means you have to write your answer in decimals. And that has to be correct to 3 decimal places. Now, what do we do then? We take square root. But remember, when we take square root, we always put plus minus. So you have 1 plus under root 3 over 2, and then square root of that whole thing. What do you get? That's 1.366602. So to 3 decimal places, this is what you have. X is equal to plus minus 1.366. Now, whenever you get multiple answers, you should generally check in the question if maybe one of those answers has to be ignored or cancelled for any reason. You are getting two answers. Let's look at the question statement. The question statement tells you find the possible values of X. That means you are supposed to have multiple answers. So you have two answers. That means they're going to be correct. Okay. You don't have to ignore anything. Okay, now let's look at part two. Part B. Now in part B, you have to solve this equation. Sine of 2 theta plus pi over 3, that equals 1 over 2. Let me write that down here. Sine of 2 theta plus pi over 3, that equals 1 over 2. And theta is between 0 and pi. Okay, this is the equation that we need to solve now. Now, notice this is in radians. We don't have a degree sign here. We have this in terms of pi as well. So that's radians. Make sure your calculator is in the correct mode. You have to use radians here. How do we solve this equation? How do we start? The first thing we have to do is we have to use a substitution. We say let A equals 2 theta plus pi over 3. Right? We could use this substitution. And now we also have to adjust the interval. So this equation would actually become this after using substitution. It becomes sine of A equals 1 over 2. It's just as straightforward as this now, right? Sine A equals 1 over 2. However, you also have to adjust the interval. Interval for theta is from 0 to pi. What about the interval for A? What would that be? You input these values here. You input 0 in this. You get 2 into 0 plus pi over 3. What's that? Pi over 3. So the lower limit here is going to be pi over 3. Then what you do is you input pi. That gives you 2 pi plus pi over 3. Put this on your calculator. Calculator will do the LCM for you. That's 6 pi plus pi is 7 pi over 3. Let's say 7 over 3 times pi. And here it's 1 over 3 times pi. That's the interval that we've got. Pi over 3 or 1 over 3 pi, it's the same thing, right? That's the interval for A. So when you're solving this equation now, when you're looking at quadrants and looking for the angles that are possible, keep this in mind. You are going to have to look for values in this interval. And remember, when you're talking about radians, the values on these axes are 0, pi over 2. This is pi. This is 3 pi over 2. And then this again is 2 pi, and so on. I'll give you 2 minutes. Give me the values of theta quickly. Tell me what the answers turn out to be. Take 2 minutes and find out the solutions for this. Find the basic angle, find the possible angles, then use the substitution that again. Put A equal to 2 theta plus pi over 3 and find the values of theta from that. Do this quickly. Tell me the answers in the chat box quickly. Yes, anyone who's done, can you tell me the answers in the chat box? Arham, Aisha, Hera, Naima, Rizal, I'm waiting for your answers. All right, good. Let's try this. So we start with finding the basic angle first of all. Okay, let's find the basic angle first of all. We say sine of alpha equals 1/2, right? What's the basic angle? Remember, your calculator has to be in radian mode. So the basic angle is going to turn out to be pi/6. Okay. Now sine is positive. Sine is positive in the first quadrant or in the second quadrant. These are the two quadrants where sine is positive. So it's either here, this is alpha, or this is alpha. So say this is pi/6, or this is pi/6 here. Now, where do you start measuring angles from? Positive x-axis. So you start measuring angles from here. The first angle that you get, the first value that you get for A is pi/6. But now you have to note, and you have to check whether that is in the interval. The interval is starting from pi/3. Pi/3 is bigger than pi/6. If you're confused, you can compare the fractions 1/3 and 1/6, right? 1/3 is where it's starting from. 1/6 is what you have here. 1/6 is clearly smaller. 1/3 is bigger. If you are unsure, just do this on your calculator. Put pi/3 on your calculator, that will give you 1 point something. Do pi/6, that will give you 0.5 something. So clearly, pi/6 is smaller. That means it's not in this interval. It does not fall in this interval. So you do not have to consider that. Okay. So we can't consider that first angle. We go here instead. That's the first angle that we get, pi minus pi/6. That's 5 pi/6. You can see that is bigger than this. So it does fall in the interval. So the first value of A that we're getting is 5 pi/6. Okay. And then since 7 pi/3 is greater than 2 pi, you can check that. 6 pi/3 is 2 pi. So 7 pi/3 is of course bigger. That means you can go one full circle and come back again as well, like this. This is the next angle that you get. You have to check whether that falls in the interval or not. You can check that 2 pi plus pi/6. What does that give you? That gives you, you can do this on your calculator, put this on your calculator directly. That will give you 13 pi/6. Now, does that fall in the interval? You can do that on your calculator. You can do this using what you used to do in O-levels, making the denominator the same. That's one idea. This is 14 pi over 6, and this is 13 pi over 6. So of course, 13 pi over 6 is supposed to be smaller, right? That means it does fall in the interval. If you find that difficult, put this on your calculator. 7 pi over 3. See what your calculator gives you for that. 7 pi over 3 in decimals is 7.33. And 13 pi over 6 in decimals is 6.8 something. So that means this does fall in the interval. Okay? So this is the next angle that we're getting. 13 pi over 6. Now we put that substitution back. We can't find any other angle. You can try that. You can go one full circle and come back to this again. But that's going to be outside the interval. Okay? You can check that as well. These are two values of A that we have. Now we put that substitution back. What was A? A was 2 theta plus pi over 3. So we say, okay, let's replace A with that now. 2 theta plus pi over 3. And now you can find the value of theta from this. So the first equation is this. The second is 2 theta plus pi over 3 equal to 13 pi over 6. Solve these two equations to find the values of theta. You solve the first one. That gives you 2 theta equal to 5 pi over 6 minus pi over 3. That's going to be, again, do this on your calculator. 5 pi minus 2 pi, that's 3 pi. 3 pi over 6, that's pi over 2. So the value of theta turns out to be pi over 4. That's one answer that you have. Do the same thing on the other one. Take pi over 3 to the other side. 2 theta equals 13 pi over 6 minus pi over 3. And that gives you 11 pi over 6. And then theta equals 11 pi over 12. These are the two answers that we have. And yes, that's correct. Naima and Hazem, both of you got it correct. That's what we have. Okay, these are two values of theta that we get from this. Is that okay? Any questions on this? Any questions on this, anyone? No? All right, great. So make sure that you do more questions from the worksheet. On Thursday, we will be doing the last major, no, not the last, another important concept. We would still have graphs left after that, but on Thursday we'll be doing another concept, and we will learn how to solve equations that look like this. Not equations, questions that look like this. Question number 43, for instance, where you have one function given, like you are given cos of theta here, cos of x here. Cos of x is p, question number 43. And using that, you have to find sine x, tan of 90 minus x, for instance. You'll find other questions like this as well. For example, this one, 46. You have a reflex angle theta, such that cos theta equals k, and you have to find sine theta, tan theta, and then sine of 2 theta, explain why that is negative. And there are other questions like this as well. Okay. So in the next class, we will learn how to solve questions like these, for example, 49 as well here. Okay. That's the plan for the next class. You can try some of these to understand maybe if you can solve them somehow using identities that we have done until now. But there are some of these parts that you cannot do using identities. We will be discussing them in the next class, inshallah. Okay, so make sure that you do practice. I'll see you again in the next class. Allah Hafiz.